We'll start with common strategies and performance pitfalls. This list is by no means exhaustive, but it represents a lot of experience we've had over the years. Don't block the EDT. This is the number one performance tip. If you have one takeaway from this, it should be this statement. The event dispatch thread is the thread that is invoked for every listener, event, or paint operation. It does everything in Codename 1. The EDT runs a cycle that's supposed to finish well below the 16 millisecond mark. That's important because the EDT is only one part, and after it is done, the native thread needs to perform some work as well. If you perform lengthy operations on the EDT, such as parsing, you might see a performance penalty. To be fair, we do these things too. A lot of our demos perform some parsing and image loading on the EDT. Most APIs must be invoked on the EDT, which makes it hard to avoid blocking it. The core workaround for this penalty is to delegate work into another thread. We can do this with the network manager, which implicitly uses the network thread for communication. You can also open a thread to do intensive work and return to the EDT with a call serially invocation. A simple example of this would be something like this. We launch a separate thread to run slow code and then return the response to the EDT with call serially. One approach to offload processing is invoke and block, which spawns a thread while blocking the EDT in a non-disruptive way. This makes development very convenient as you can avoid nested callbacks. However, invoke and block is more expensive in terms of performance than a regular thread and callback approach. So if you are concerned about performance, invoke and block might not be the best option. These concerns should also apply to the add to queue and wait method from the network manager, which would also incur a similar cost. One of the tricks I did in the Uber application for features such as shadows was leverage the call serially on idle method. This method works like call serially, but it invokes the code only when the EDT is idle. Idle state happens when the EDT is ready to sleep and doesn't have too much to do. Initially, I rendered the component without a shadow and added the shadow after the fact using a call like this. Threads aren't magic. This is somewhat contradictory to the recent statements, but threads aren't enough. Developers often perform a slow operation on a thread only to discover that rendering is seriously impacted. Mobile CPUs aren't as fast as people think, and they are bad at task switching. If you spawn a thread that takes too long and uses a lot of CPU resources, it will starve the EDT and potentially cause rendering to be sluggish as a result. In fact, we force the EDT to sleep with every cycle, so it won't starve the native rendering thread. The solution is to explicitly yield the thread occasionally if you don't do I/O. Notice that if you are reading or writing to a stream, the underlying kernel stream reading code should yield the CPU for you. Assuming you have a long calculation, you can just sprinkle util.sleep1 or even longer through the thread code to make sure the CPU delegates time to other threads. While we are on the subject, I'd like to say a couple of things about thread safety. Creating threads is important, but performant synchronization is often challenging and error-prone. It might negatively impact the performance benefit delivered from threads to begin with. One of the advantages of the single thread approach in the EDT is that we can avoid synchronization almost entirely within the Codename 1 code. This reduces overhead noticeably, as synchronization is a very expensive operation that can't be optimized by a compiler and even impacts JITs. If you need to use a thread, I would recommend the EasyThread class, which simplifies the process of communicating with the EDT in a way similar to call serially. Caching is at the core of almost every optimization you will make. Caching can be as simple as keeping a value in a variable, or as complex as weak references with purge strategies. A core decision about caching is where to cache and what to cache. Let's say I have this code. Should we cache the image or should we cache the label? There is no simple answer. Normally, I wouldn't cache the label, preferring to cache the form, but the logic of image caching is tricky. If I keep an image and then create a scaled version of that image, I'll effectively have two instances of that image in RAM. The only tip I can give about this is awareness. Look at the things you cache and try to avoid caching in the wrong place. Notice that a 2 GB RAM device doesn't allocate that RAM to the application. The application gets far less, and this should be further restricted as device OSs kill applications that take up too much RAM. That brings up a common question. Should we reuse form instances? In the past, we used to recommend that developers discard form instances once they were done with them. Then, if they needed to go back to the form, they could create a new instance. This was the strategy in the old Codename1 GUI builder, and it has advantages in terms of RAM usage. However, it makes some things very hard to code, going back to the exact previous state of the form, and it is arguably slower in terms of performance. Today, for the most part, we advocate the reuse of form instances, but not dialogues, which are more transient by nature. The logic behind reuse relates to the amount of RAM available on the devices and taken up by a form. It should be okay for the most part. The problems start with forms that contain many images. In those cases, we need a strategy to purge memory when leaving the form. There are some elements that might be expensive to cache, such as images. In these cases, we want to cache the data for the performance benefit, but if we don't have enough RAM, we'd rather discard it. This is in fact the strategy taken by Encoded Image, which I'll discuss later. JavaSC has built-in classes that cover a lot of the details, such as weak reference, soft reference, etc. Unfortunately, soft references, which are the most useful option, aren't available. The solution is available in the CN class. JavaSC also offers weak hash map, which we refactored into com.codename1.ui.util. It uses the soft references built into Codename1. This class is essentially a regular map that can lose its value objects when memory gets low. Another common class for caching is the cache map. Unlike weak hash map, it caches data and saves extra data to storage. So it's meant to cache data that you might fetch from the network or a similar source. It makes sense for larger elements or for small cached data. I would just use the preferences.